Hello, everybody. Welcome to the Thursday edition of Quantum Mechanics, Week 7. Upcoming announcements, not really much to talk about other than the lab that we talked about yesterday in the lab lecture is due next Thursday on June 4th. So not today. That would be a very short amount of time to do that lab. It is very Excel/Google Sheets intensive, so be sure to watch the video where I go over how to enter all those commands, and then check to make sure that your numbers match up with mine for the first few columns so that you know that you're doing it right. There is a non-zero chance we might finish quantum mechanics today, so let's get straight to it. I left you with an introduction to ionization energy where I drew a picture of what ionization energy looks like, and if I had thought to draw that really quickly beforehand, I would have done so. But I did not. Oh, I need to put this on the right layer. Hold on. Anyone who uses Photoshop or any sort of art program knows all about drawing on the wrong layer. So, if I have my energy diagram here, and here's n equals infinity. Here's the nucleus. And I'm just going to put some orbital in here. It doesn't matter what this is. Moving my electron up to n equals infinity represents the ionization energy. And so for this diagram, however much energy this was to get from here to here would be the ionization energy. Now, while I have the diagram here, let's do the opposite. What would happen if I were to put an electron and I were to allow it to fall into this spot? What that would be is actually something called electron affinity, and that's what we're going to do in the second half of the first hour today. Oh, shoot. Yeah, I closed a window. Hold on. Window capture. Yeah. Nothing in there is useful because my stream key is blacked out, so you can't just pose as me. There we go. That's what I want it to be. Oh, never mind. That's the wrong window. I can fix that one later. Chat log. There we go. That sometimes happens. Yeah, there you go. Thank you for noticing that. Is this one okay? Yeah, this one's okay. Yeah, for some reason, OBS doesn't capture the chat window the first time every time, so I always have to pre-program it. And then if I don't click every scene, like these are scenes, like this is the scene, this is a scene, this is a scene. Technically, this is a scene, but I don't know if you can see that. But yeah, so like it doesn't always capture all the things, and sometimes it's weird. Anyway, I don't even know where I was. Oh, I was talking about electron affinity. We're going to talk about electron affinity later in today's lecture. But right now, we're going to focus on ionization energy. And so you can see that ionization energy is always going to be a positive number. Oops, wrong color, but that's okay. Ionization energy is always going to be a positive number because I had to put energy in. Electron affinity, on the other hand, it looks like it's always going to be a negative number. And if electrons actually stick, then it is. But there are some exceptions where electrons don't want to fall down and be put in an orbital. So, let's see here. Where am I going? I want to go back to this screen. That's what I want. All right. On this slide, we're going to try and explain everything that we can about this slide. Starting with why... Oops, I meant to draw on that. Instead, I clicked forward. Why noble gases have very high ionization energy. And why anything in like the far left of the periodic table has very low ionization energy. Now, if you've taken a chemistry class before in high school or maybe 140, you probably know about how elements that are on the far left of the periodic table want to give away their electrons. And so ionizing them must be easy. and how elements on the right side don't want to give away their electrons. They want to take them instead, so ionizing them must be hard, since it's the opposite of what they want. And quantum mechanics is going to explain that. But we also have some weird anomalies. So we've got this thing going on. What are these little dips that the third element in a period always has a lower ionization energy? And so there's a sixth one. Like, what's the deal here? We'll try and describe that today. Ionization energy is kind of like atomic radius. If electrons are held tightly by the nucleus, they are then closer and have a higher ionization energy. Now, they're not exactly the same because of things like orbital penetration and stuff like that. But they are pretty similar for the most part. So you can make an analogy that, oh, if my electrons are really close to the nucleus, they must be harder to ionize. And generally speaking, that will be correct. So the same two principles that guided us for atomic radius are going to guide us for ionization energy. We're going to look at the maximum N, and then we're going to look at Z effective. And hopefully everybody remembers how to calculate Z effective, because we're going to do that again today. That's what I wanted to do. Okay. If an electron is further away, it is easy to take it because it is not as strongly attracted to the nucleus. So remember Coulomb's law, which is, and I gotta get the pen out here, so E is proportional to Q1, Q2 over R. If I make R really, 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 really big, then the activation energy, or not activation energy, ionization energy approaches 0. And as it gets lower and lower and lower and lower, then the electron is essentially just bloop. We can just pluck it right off. Now, if I have all of my electrons in the same sublevel, then depending on which atoms I'm comparing with electrons in the same sublevel, the one with a higher Z effective has a higher Q. And so if this number increases, then this one also increases as well. So atoms that have higher Z effective will hold on to their electrons more tightly, and thus are harder to ionize and remove the electrons from. So going back to our diagram here, that seems to make sense. As I go between rows here, so this is period 1, this is period 2, period 3, period 4, you'll notice that the ionization energy goes down because those electrons in the valence shell are getting further and further away. But as I go across a period, right here, so this is my period. What? I don't know if you could hear my cat. She interrupted me. I apologize for that. If you go across the period, you'll see that here's lithium. It has Z effective of +1. Beryllium is +2. Here's +3. And I'm just going to write the numbers here. 4, 5, 6, 7, 8. And you can see, generally speaking, going across the periodic table increases the ionization energy, with 2 exceptions. And those exceptions are where I have those blue arrows from before. What do you notice about the ionization energies of all my transition metals in these periods here? Would you say that they are increasing very greatly, remaining roughly constant, or there doesn't seem to be any pattern? And once you have made a decision on that, why do you think that is? Type the reason that you think in the chat, based on what we talked about with transition metals and their Z effective on Tuesday. So it does look pretty much constant, and I would agree with that. What did we say Z effective was for a transition metal, at least in this class? Ignoring Slater's rules and all the crazy fine granularity that they bring. Good. Z effective is just 2. Yeah. Because the only valence electrons on those elements are s electrons. The d electrons are not valence electrons. They're not in the highest level n. And for our purposes, that's good enough. We'll count d electrons entirely as shielding electrons. Alright, so how do we explain these blue arrow things here? What I'm going to do is first I'm going to clear the screen here. Boop. And we're going to identify these elements first. So this is beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. And then what I'm going to do is we're going to go to this screen. And we'll do that. That works. Alright, and I'll draw over here. So let's draw a generic diagram. So here's the nucleus. We've got 1s, 2s, 2p, 3s. And this keeps going, and that's fine. And I'm going to put n equals infinity right here. And then let's throw our electrons in here. So for lithium would look like this. And then beryllium would look like this. But remember, as Z effective increases, all of the orbitals that have electrons in them get shifted down. And of course, I can't make it do that super easily. So here's what beryllium would look like. It'd actually be a little closer to the nucleus. Now I need to put in boron. And now I want to determine the difference in ionization energy between beryllium and boron. So beryllium was harder to ionize than lithium because adding this extra electron also added a proton in the nucleus, and so everything gets pulled tighter towards the nucleus. But my next electron for boron went in 2p. So with that in mind, which is harder to ionize? I'm trying to find a good color here. Is it the electron that I added for beryllium? That was not the color I meant to select, but that's okay. In fact, let me just actually choose that color. There we go. Would the electron for beryllium be harder to ionize, or would it be harder to ionize boron? It's harder to ionize beryllium because it takes us more energy to get it to n equals infinity. And the reason for that is because boron is the first element that the electrons go into 2p for. And 2p is higher in energy than 2s. So it must be easier to ionize 2p. Now when I add those electrons in, again, everything shifts down. I'm going to run out of space at the bottom there, but that's okay. And then when I add my next electron for carbon, it's harder to ionize than boron was. And then everything shifts down. And, oops, sorry, I put it in the wrong spot. I meant to put it there. And then everything shifts down, and then I just keep doing that. So now we'll get to nitrogen. This is what nitrogen looks like. And what I actually want to do is erase this one. Actually, you know what I want to do? I want to draw the whole thing over again. Because I want to have these side by side for this example. Alright, so I'm going to have nitrogen. Here's nitrogen's nucleus, and here's oxygen's nucleus. And I'm going to put the electrons in, so nitrogen looks like this. And oxygen looks like that. Where there's this extra electron right here. Now, looking at the ionization energy curve, nitrogen is harder to... Or, I'm sorry. Nitrogen is easier to ionize. I can't read the numbers. That's my problem. I'm reading it upside down. Nitrogen has a higher ionization energy than oxygen is. So this one is easier to ionize. And this one is harder. Can you explain why using quantum mechanics and the diagram? And again, remember, we're trying to get to n equals infinity. Now, the answer is not, oh, you drew the line closer to oxygen because you can't draw on your tablet. Assume that's a straight line. But why would it be easier to ionize oxygen? Is there anything that could help it? I'll give you a hint. What's the difference between nitrogen and oxygen in the diagram? So the difference is the extra electron, but what about the extra electron? Because when I went from carbon to nitrogen, I also had an extra electron. But the ionization energy just goes up. So why did going from nitrogen to oxygen and getting another extra electron make its ionization energy go down? The repulsion of electrons, closer. But all electrons repel. Can you be more specific with your answer? It can be given away without changing it. Not quite. Not quite. But you're very close. Electrons are not repelled from the nucleus. They're actually attracted to the nucleus. What's the only difference between these two diagrams outside the nucleus? Oh, we're very close now. The electrons have opposite spin. What else do we have there? Think about where those electrons live in space. All right, we'll give you a hint. What does this box represent? Because obviously that's the difference, right? One of these boxes is different than the other, and it's this one. So we can pin that one down. So that's an orbital. What is an orbital? An orbital is a region in space that electrons live in. And they're somewhere in that orbital. And yeah, it's part of an energy sublevel. It's part of an electron cloud. What's different about the orbital I put an arrow on than all the others in the 2p row? I'm sitting here biting my tongue because I feel like it's really obvious, but I guess there it is. That's the orbital with paired electrons. You got it. What do paired electrons do to each other? We made it. They repel. So this is the first instance in 2p where you put electrons in and you have to force them into a paired orbital. And even though paired electrons are allowed because they have the magnetic attraction, they still repel each other. And so if you're trying to ionize this one right here, The other one kind of gives it a little push, like, hey, here you go. Yeah, you guys are totally overthinking it. And I feel like that's a lot of quantum mechanics, is that it feels like everything is super complicated and like you're going to overthink it, but really, quantum mechanics cares about three things. You can describe pretty much everything in chemistry with those three things. And so that's actually what I want you to be doing when you consider these sorts of orientations. Like, okay, I've paired this for the first time, so it goes down. Oh, I went to the next energy level, so that's higher in energy. Okay, so it goes down. That sort of thing. That's why it drops between Br and... I'm going to assume that you meant Be for beryllium. But for lithium to beryllium, there isn't an opportunity to do electron-electron repulsion. Mostly because the 2s orbital is just not that small. So remember that a 2s orbital is like a sphere, but a p orbital is something like that. And the effect is actually already accounted for in the drawing. I'm going to go back to the drawing and kind of draw on it, so hopefully that this will become more clear. Oh, that's not the command I wanted to do. I wanted to do that. All right, so here, this first dip that we see, these dips are due to us going from S to P. And I think a better answer to explain why it drops from here, this is the best answer, but the adding an electron between these two, so between lithium and beryllium, there isn't a second degenerate orbital to put it into. And so when you put the electron into the first orbital, it gets attracted to the nucleus and the orbital goes down. When you put the second one in, you're also putting a second proton, and so even though there is repulsion, the electrons are still attracted to the nucleus, and there's nothing really shielding it. So I think that those effects more or less are equal. At least for this diagram, because this slope appears to be pretty constant. Minus this little dip here for going from S to P. And then this second... oops, you know what? Let me do a different color here. The second dip is due to... That's the wrong pen. Electron-electron repulsion. Now, it doesn't always dip because this is what should happen. Is this dotted line here. The effect of electron-electron repulsion is to lower it by this amount. And so, if there was no electron-electron repulsion, we just slide that whole line segment upward. But because electrons are now pairing after that, everything gets to benefit from that. And then finally over here, we said that these guys have a roughly constant Z effective. And same over here too. And that's the chart. We have basically explained every instance of interest on the ionization energy chart. So on an exam or quiz, what you'll be asked to do is to tell me what it means to ionize something, what it means to perform electron affinity. And then I might show you this chart and ask you to explain deviations between two different things. And that'd be in like a multiple choice or fill in the blank sort of format. All right. So let's do the examples. Without going back to that chart, which has a higher ionization energy, oxygen or sulfur? In order to do this, you're going to need to pull out the periodic table, and you're going to treat this just like atomic radius, really. Figure out what ends are, figure out what the effectives are, and then make your conclusion based on that. So I'm going to give you 2 or 3 minutes to figure this out. I got to go grab my phone because it's charging, so I know what time it is. And then when we come back, we'll go over the answer. Type your answer in the chat when you think you got it. My cat is in here meowing at me again. How are we doing? I see some answers. Now remember what ionization energy is. So whenever you're being asked which is the higher ionization energy, that means for which atom do you have to lift the electron higher? Because what I'm worried about is that people are going to look at this question and go, oh, I'm going to pick the one with the higher radius. Because they're similar, but the answer that you're going to get at the end is different. So consider that perspective, and then consider my poor cat, who is so sad and alone. I apologize if you can hear my cat in the background. I haven't pet her for hours, and she is just rock bottom. Alright, so we're going to draw our picture here. So there's our nucleus. Now these should be lower in energy on this side, but it's hard for me to draw these in here, so. And so if I draw my electrons in for oxygen, oxygen has 8 total electrons. And it'd look like this, but sulfur has 16. Alright. Who is harder to ionize, and thus has the higher ionization energy? Well, if I took an electron from oxygen, it'd be right there. If I took an electron from sulfur, it'd be right there. So who did I have to ionize more energy for? And the answer is oxygen. So there's oxygen's ionization energy. And it's bigger than sulfur's, because I had to lift the electron up more. Now, the numeric way to do this would be to consider the following. So, if I look at oxygen and sulfur, and I look at their N, that should be an M there, and I look at Z effective. And if you count Z effective for each of these, you're going to get the same result for both of them, because oxygen has an atomic number of 8, and there are 2 core electrons. Sulfur has an atomic number of 16, and there are 10 core electrons, the neon core. And then the maximum N that each of these have, well, oxygen's in period 2, and sulfur's in period 3. So for this question, what I would do is I would say, oh, look at this, I have a higher N for one of these. And my conclusion would be that higher N is electrons farther from the nucleus, which makes them easier to ionize. But I don't want easier, I want harder for this question, which is the higher ionization energy. It must be oxygen. And there you go. So that's the thought process that you should be going through here. Again, look at Nmax, look at Z effective. Try and find exceptions. Would the one with the higher atomic number always have less energy? No, because we're going to do that on the next example right here. Oh, no, not that example, because that's a different example. But I could do one for that. So let's erase. And if I asked you to do these 2 atoms, and I said, which one has the higher ionization energy? Which would it be? So who has the higher ionization energy? Aluminum or silicon? I'll give you a hint. Consider the same things that we've been doing all along. Any guesses? And a reason, if you have it. Does it have a higher N? What is N? What is N? So N is 3 for silicon, but it's also 3 for aluminum. What does N represent? Now we're just throwing words out here, aren't we? N is the principal quantum number, which is the energy level, which represents distance from the nucleus. It's the most coarse description of distance from the nucleus that we have, because the energy levels are spread apart, and then the sub-levels within that subdivide the energy levels. So we gotta know our terminology. Next, for paired electrons, are there any paired electrons in aluminum in the p orbitals? If I draw 3p for each of these, so for aluminum, this is what I get, and then for silicon, I get this. So can't be that. Those orbitals are degenerate. Give you a hint, I haven't filled it in yet. That's the answer. What's the effective for both of these? It is higher for silicon. What is it for silicon, though? Very good. What is it for aluminum? All right. So why does this having a higher Z effective mean that this has a higher ionization energy? Use quantum mechanics to explain your answer. So I like Leia's answer better, because that's more what this is describing. So this is the pull from the nucleus. Nucleus. I don't know what I was spelling there. Nucleus. And if the nucleus pulls those electrons stronger, those electrons are held on more tightly, and thus they're harder to ionize. And it's because of the extra proton between aluminum and silicon. That's right. Now, if there were more valence electrons, which there are in silicon, and there was less pull from the nucleus for each electron, then we would see the opposite effect. But that's not what we see. What we see is that ionization energy is higher, so the effective Z effective must be better than just adding more electrons. So be careful. All right, let's do another one. And I have it on the next slide, I believe. Or I have it on this slide, is what I mean. So I want you to look at these two. Phosphorus or germanium? Which one has the higher ionization energy? Now, only one of those is the right answer, and there should be 2 reasons why that is. And I want you to list both of them. The elements on the top on the slide here. So phosphorus or germanium. Can I circle these? I do this. The ones that are in yellow at the top. I didn't want to erase the rest of the stuff on the screen because you might use it to help you do this problem. Oops, I didn't mute my mic. I'm watching videos on Discord while I'm waiting for you guys to give me an answer. I have a friend that is constantly sending me videos of pet pigs because I wanted to adopt a pet pig when I get a house. And he linked this video of a pig, and there's video or audio in it, and it was apparently a woman laughing as the pig tried to climb on the couch and couldn't because he's too tiny. If I knew how to link off of Discord, I would put the link in the chat so you could all see a pig jump on the couch, I guess. No, I love pigs. Pigs are so cute. I grew up on a farm, so I like all the, like, stupid pets, I guess. I don't know. We had a rooster when I was a kid, and he just run around and, like, peck my brother, and I really liked him. Because I hated my brother. Go get him, rooster. Alright, so we're going to go over the answer. Hopefully people have decided upon one of the two. here. So let's do this. And then we'll go N max Z effective. Now that's totally fair. If you work with like X, Y, or Z for a career, then you'll hate it. Or if you live next to it. So like for example, I used to live next to a what was it? It was like some sort of hamburger chain, but like it was a very specific like smell from their burgers. I don't even remember where it was. It was a long time ago. But now whenever I like go past that and I smell like the nauseating smell of French fries and the specific hamburger patty that they were cooking, I just like, oh, I do not want their burger ever again. I love hamburgers, but I cannot go to certain restaurants for that reason. All right, so let's write down these numbers here. So what is the max N for phosphorus? It's in period 3. So we get that. Where's germanium? It's in period 4. And then I need to calculate Z effective. What's the effective for each of these? So what's the Z effective for phosphorus? 5, good. And then how about for germanium? 4. All right. So we can count Z effective effectively. That's good. So now what we should do is let's look within each attribute and choose the one that has the higher ionization energy. So what's harder to ionize? Something with N equals 3 or something with N equals 4? And it would be this one. Now let's go down to Z effective. Which is harder to ionize? Something with Z effective 5 or Z effective 4? Which pulls the electrons closer? Yeah, there you go. So this must be the one that's harder to ionize, and it turns out that that totally is right. So if you were asked to describe this using quantum mechanics, I would say electrons in N equals 3 are closer to the nucleus, and Z effective of 5 plus holds electrons tightly. Therefore, it has a high ionization energy relative to germanium with N equals 4 and Z effective 4 plus. All right, so we got that one. So now what I want you to do is tell me which of these elements in each pair have the higher ionization energy. So we've got Lena, we've got Erbser, Icy, and Fs. And on all of those pairs, you should be able to pick the higher ionization energy of the two, with one exception. And on the exception pair, what I want you to do is just identify, oh, I can't pick the answer. It's impossible to determine. Okay, so I'll give you about 5 minutes to do that. We'll go over the answers. We'll take a break. I'm going to go watch more videos of pet piglets, because that's apparently all that they're linking to me now. Ooh, I can write the formula for Z effective on the screen here. Not with the highlighter, but there you go. So it's the atomic number minus core electrons. All right, how are we doing? Do we need more time? Should we go over the answers? What would you like to do? All right, so let's compare these and see what we can discover. So we have Lena. We're going to compare the maximum N and Z effective. For lithium, that's 2, and sodium, that's 3. And if I count their Z effective, I get +1 for both of them. Now I want to find the one that's harder to ionize. What's harder to ionize? N equals 2 or N equals 3? Which one requires me to get the electrons to move further to go to N equals infinity? There you go. And so this one must be harder to ionize. We'll do the same thing with rubidium and strontium. What N are they in? 1, 2, 3, 4, 5. 5. And then what's their Z effective? Alright, which one's harder to ionize? And why? Well, the difference is down here. And strontium has a stronger attraction to its nucleus. Its valence electrons do anyway. So strontium must be the one with the higher Z ionization energy. That must be iodine, right? Iodine and selenium. But Rb doesn't have a stronger pull. It has a 1+, whereas strontium has a 2+. So where are iodine is? There it is. Okay, so 2, 3, 4, 5. So looking at N max, that's 5. Selenium is 4. And then this is 6, and this is 7. So looking at this one, electrons that are closer to the nucleus are harder to ionize. So lower N, but Z effective that's higher is also harder to ionize. So I have 1 in each column. Who's the winner? And the answer is we can't tell. So if you get in a situation where one detail indicates one element and another detail indicates the other, it's not possible to differentiate the answer without just looking it up. You have to actually do the experiment. Or you need more criteria. So this is the impossible one. And the impossible one happens because Nmax supports selenium, but Z effective supports iodine. And it's not possible for us to differentiate that without going into more detail. And then finally, fluorine and sulfur. N is 2, N is 3. Z effective is 7, Z effective is 6. And there you go. Fluorine is the harder to ionize. It has a higher ionization energy. While you were on that problem, I was telling all my friends about the baby pig video, and they were like, well, why don't you just link it to your students? And I was like, oh, I can do that. So here is the baby pig video that was linked to me, which you can watch during the break that we're going to have right now. So I'll put the timer on the screen. I don't have a timer yet, so it's not going to do anything. There we go. Oh, no. Hold on. So I'll start the timer, and you can watch a pig video for 10 minutes. It's like 20 seconds long, and you'll hear the woman giggling. But I'll turn the music on, and we'll see you in just a bit. Oops, I looked up and I saw it just cross over to 10, and I was like, oh, I missed everything already. I was playing around in my stream settings trying to figure out something. Turn that off. Turn that off. All right. So we've already talked about these exceptions, so I'm going to skip over them. But let's continue on to talk about ionization energy number 2 for different elements. Because the next pattern that we're going to talk about involves us determining whether an atom has valence electrons that are being ionized or core electrons being ionized. And generally speaking, you can tell this by looking at ionization energies. The first thing that we want to note is that the second ionization energy is always larger than the first ionization energy. And now it might be a little larger, or it might be orders of magnitude larger. Now, what you're going to try and look for when you look at data are for huge jumps in ionization energy. And this occurs if the electron that's being ionized was a core electron at the start. So what I mean by that is, like, if I had sodium is one valence electron. So if I tried to ionize a second electron away, the second electron I would be taking would have been originally a core electron. When you do that, you see a giant jump in energy. So for instance, here's sodium. It's 496 kilojoules per mole to ionize the first one. But it's 10 times more to get the second one because the second electron being taken is a core electron. Magnesium has 2 valence electrons, and taking them is not relatively difficult, but getting that next one is extremely difficult. So when you see the giant jump in energy, and that means that the ionization energy goes up by like times 5 or times 10. What that means is that you have ionized away a core electron, and that all the electrons prior to that must have been valence. So if I gave you an unknown atom, you could actually tell me what it is if I tell you what period the atom's in, and I give you enough ionization energies for you to see the pattern. So here are a bunch of atoms that I'm going to leave this for you to rank in an order of increasing ionization energy, because we just did this. This is the one that I want you to actually do. So first I want you to... Oops, sorry, I hit the spacebar because I dropped my pen. First I want you to explain why cesium metal is more explosive than sodium. You might remember at the start of the quarter when I was talking about laws and theories and stuff, and we dropped elements into water and they all exploded, that cesium exploded much more readily. Why is that? Using quantum mechanics. And I'll give you a hint. The reaction requires the metals to become cations, but when they're metals, they have all of their valence electrons. And then in the table down here, tell me what the mystery element is if all of the elements are in period 3, based on the data that you see. So I'll give you a few minutes to do that. All right, let's go over the answers, because I'm going to run out of time if I don't. So, why does cesium explode more than sodium does? And it turns out that the answer has to do with ionization energy, because of course it does. It's in the ionization energy section, right? So we'll get to this one in a second here. So you might have remembered that when we dropped sodium into water, and yeah, the mystery one is aluminum. We'll talk about that in a second. When we dropped elements into water, sodium fizzed for a bit and then it caught on fire, but cesium immediately exploded. And the reason for this is because for sodium, its highest electron was in 3s. And so it took this much energy to ionize, and that energy was gained from water, from just the ambient energy that's in water, so like thermal like collisions and stuff like that. But cesium has an electron in the 6s orbital. So its ionization energy is much, much lower than the ionization energy for sodium, which means that when the electron is removed and the reaction proceeds, any excess energy goes toward perpetuating the reaction. And so sodium takes a second to ramp up, but it eventually starts burning. Cesium explodes on contact with water. It immediately detonates. And that's entirely because the ionization energy of cesium is so much lower than that of sodium. On the slide, we see that these elements have increasing ionization energies, but it's where the giant jump occurs. So here's my giant jump for sodium. So I had 1 valence electron. For silicon, there really isn't a giant jump. It would probably be right here. But none of these increase by a factor of 5. But for the third element, there's my giant jump. So I must have this many valence electrons, which means that this must be aluminum. All right. That's ionization energy, and that's all we're going to talk about, I believe, because we're going to move on to electron affinity, which is just the opposite of ionization energy, really. All right, so electron affinity is simply how much energy is the energy change, we'll say, when an electron is dropped into an orbital. Now, to add an electron to something, you set it at n equals affinity, and then it falls towards the nucleus. If it stays there, then the electron affinity will have a negative energy. In other words, energy is released. However, if the electron is repelled for various reasons, the energy that is there for that process will be positive. If the energy is positive, then what that means is that you have to put energy into the atom in order to keep the electron there. Basically, you have to provide energy to hold it in place. Now, I don't know if I have a chart to show electron affinities here. I don't. Now, the general trend for electron affinity is that the electron affinity of elements with high Z effective is very negative. And if it's a low Z effective, it's not very negative. And the reason for this is because adding electrons are going to be attracted to the nucleus. And if the nucleus has a high charge, the charge being Z effective that the electron can feel, it will be attracted more strongly, and it will want to stick more. If there isn't that much Z effective, such as, say, sodium, then there isn't much attractive force that will hold the electron on, and thus you won't get a very large electron affinity. An electron being repelled would have a positive electron affinity. That's right. And I'm going to draw that in a second, but I actually need to find the document. It is in the textbook. Where is my copy of the textbook? Atoms first. There we go. Give me just a second. I got to find the right section in here so I can put that on the screen for you. Is this electron affinity? It is. So I'm going to... Well, you know what I'll do? I'll just copy and paste it. So copy. That didn't work. Oh, it's just really tiny. I gotta zoom in. Sorry, I'm trying to get a better resolution of this. Copy, please. Why isn't this copying? Oh, it did. It just put it off of my screen. I couldn't see it. There we go. All right. This is straight from your textbook. So what this is showing is the ionization energies of various elements. And you'll see that some of these are very positive, and they occur in very specific spots, such as over here. And then nitrogen is interesting for a specific reason. We'll talk about it in just a second. Anyway, I'm going to zoom out of this so that I have some space to draw on. But if we look at Z effective here, we've got 1, 2, 3, 4, 5, 6, 7, 8. And what you'll notice is, with the exception of these columns here, increasing Z effective means that our electrons are more attracted to the nucleus. So if I go across, say, here, I start at negative 60, and I end at negative 322. And so my electron affinity gradually gets more and more negative. Now, if I go down the periodic table, as the ends get further and further from the nucleus, so remember that here's, if this is my nucleus, as these ends get further and further away, adding in my electron from n equals infinity means that I'm not going to go down as far. And so the electron affinities of these values become less negative because I'm getting less energy back when I drop my electron in. And that's generally true. Now, there are some exceptions, as you're seeing over here. Like in the middle here of the periodic table, it doesn't look like many of these numbers make sense. And that's okay. We're not going to worry about these too much. But let's talk about these exceptions. Why is column 2, 5, and 8 unlikely to take electrons? And the answer to that is because when I put electrons in certain spots, I end up with a situation where the nucleus just isn't equipped to handle that. So if this is 1s, 2s, 2p, and this is beryllium, and I add an electron in from n equals infinity, my electron will go, whee, and it'll go here, but this is a really long distance from the nucleus compared to 2s. Because remember, 2s and 2p split. And for the number of protons that are in this nucleus, this atom just cannot handle that. We have to provide enough energy for the electron to stick. So for this column right here, adding an electron, the added electron goes in the whatever p orbital it is. And it's just too far from the nucleus. The atom just can't hold onto it. It turns out the same reason happens over here in this column. If I were to add an electron to neon, neon looks like this, 1s2, 2s2, 2p6. And if I were to add an electron to neon, it goes in the 3s orbital. But that atom is not equipped to hold onto an electron that is so far away. So for, oops, I just made my window smaller on accident. Let me see if I could fix that. There we go. So for this column in anything in n equals 8, the same thing is true as in the group 2a column, sorry, group 8a column is what I meant to say over here. So we'll say same, but I apologize for writing over stuff. I'm just running out of space here. That's the same, but for the ns orbital. Probably be n plus 1s, but that's okay. Finally, we've got to explain this. Why is there this hiccup in the middle? And that hiccup is due to the fact that when you are adding an electron to nitrogen, here's what nitrogen looks like. If I add an electron, it has to go here. And that's going to be the first time it pairs with something else. And as a result of that, pairing two electrons of nitrogen, nitrogen being very small already, due to it having n equals 2, that second electron comes in and goes, oh, I don't know if I want to pair with you, because, even though the nucleus is pulling on it with a force of 5+, that electron-electron repulsion, when those electrons are so close to each other, turns out to just balance out the two effects, and the electron affinity of nitrogen is actually 0. It does not want to take an electron. Of course, you can put a little energy in and hold it in place, and it turns out that this is true for all of the elements in column 5a. They have an electron affinity that is less positive than we would expect. So those are the general trends for electron affinity. If we were to summarize these, then what I would do is at the bottom here, write out the following. So as Z effective increases, electron affinity becomes more negative. As N max increases, EA becomes less negative. And then our exceptions are groups 2A, 5A, and 8A. And the reasons for these are I'm putting an electron in a p orbital, which is too far away from the nucleus. In 8A, I'm going to the next S, which is also too far away. Oops. Speaking of too far away. Ah! I clicked off the screen. Damn it. There we go. And then finally for 5A, we're pairing electrons, and they don't want to be paired. All right. That summarizes electron affinity. So I'm going to go through the slides here and just go straight to the examples. Yeah, I hadn't quite gotten to it. Sorry. So what I want you to do is, using the guidelines that I showed you on the PowerPoint sheet there, tell me which of these in each pair has a more negative electron affinity. And so the term for that is exothermic. We're going to talk about exothermic. We already have talked about exothermic. So choose the one that has the more negative electron affinity based on these trends, and not necessarily that chart with the numbers on it, but based on the properties that I had. So again, larger Z effective means it's more negative. Larger N max means it's less negative. And if you're in columns 2, 5, or A, 2, 5, or 8A, watch out for exceptions. So try that. We'll go over the answers in about 5 minutes. How we doing? Any questions? So remember that. Where's my marker? Remember how we said that doing this was ionization energy? Electron affinity is just the opposite of that. So, if you use the effective and N max to figure out which one will the electron fall the furthest, that will be the most negative electron affinity. And electrons will fall farther when they are more attracted to the nucleus. So that requires you to consider Z effective. And if they fall physically further because of N, that will affect their electron affinity as well. And then you just have to hunt for exceptions. If they have the same Z effective, then you have to compare N instead. We're actually running out of time, so I'm going to have to go over the answers here. All right. And again, we're going to just follow trends here and not research numbers on the table here. So I want to compare boron and carbon. And I'm going to, just like I was doing with ionization energy, I'm going to compare the max N and Z effective. And let me zoom that in a little bit and move it over. So these have the same N. Boron has a Z effective of 3. Carbon has a Z effective of 4. Looking at N max, where's my electron going to fall further to? N equals 2 or N equals 2? Or is that just the same? No, it's the same number. They're the same. So this is kind of a wash. Which is the electron I'm going to add going to be more attracted to? Positive 3 or positive 4? Positive 4. So carbon must have the more negative electron affinity. And if we go back to the numbers and look at that, it turns out that that's right. Boron is minus 23. Carbon is minus 123. So carbon is more negative. Let's do the next one. Sodium or potassium? There's our N max. Here's our Z effective. We're both going to be equally attracted to a +1 nucleus. But which one is the electron going to fall further to get to n equals 4 or n equals 3? Well, if it's going to fall further, it's got to go to a lower energy level. So this one should be the more negative electron affinity. And if we look at it, they are within 5 of each other, but sodium is more negative. Just like last time, one of these I'm going to have, it won't be possible to compare them to. Oh, I did this again. Hold on. Damn it. Because I keep touching the ruler. Alright, silicon and phosphorus. Let's consider their Nmax. That's just 3. When I consider their Z effective, who is my electron going to be more attracted to? Well, that's going to be not either of these because they're the same, but it is going to be more attracted to a 5 plus over a 4 plus. But what did we say about 5 plus? 5 plus was one of the exceptions, right? So therefore, this guy's the winner. So you can see the basic thought process that I go through to solve these. Compare N, compare Z effective. Pick the ones that cause the electron to either fall further, because it will release more energy when it does that, or be more attracted to the nucleus with a bigger Z effective. And then check to see that you don't land on an exception. The exceptions are columns 2, 5, or 8A. This is in 5A. So it's an exception. It's not going to be the one with the most negative. All the exceptions are more positive. Same thing with this one. This one looks pretty straightforward as well. Where you go, oh, okay, they're both in period 3. Oh, this one's plus 2. Oh, this one's plus 3. Hey, we have a winner. Actually, that one is pretty straightforward. I was comparing the wrong two. This one is the exception. Sodium has a more electronegative, or not electronegative, sorry. Sodium has a more negative electron affinity because all electron affinities represent electrons falling down, which means they're all going to be negative. Which one falls down further, n equals 3 or n equals 4? And if I draw a picture of that, if this is where my electron is falling to, this falls to n equals 4, this falls to n equals 3, this one fell further. Remember, it's falling from n equals infinity down to where it will go. It's the opposite of ionization energy. Yeah, so you'll never actually fall to the nucleus, because if an electron landed in the nucleus, then what would actually happen is nuclear chemistry, which we don't get to talk about in this class, unfortunately. But electrons never fall all the way to the nucleus. Hey, I have good news. That's pretty much it for quantum mechanics. The rest of the stuff is just like, hey, here are some trends that we can talk about. And we're going to do this section today just because it's short. I can actually do it in like 2 or 3 minutes. So let's talk about the periodic table. Did I skip 2? Oh, I did skip 2. Look at that. I didn't even see those 2. I don't know what I was thinking. Yeah, I totally did skip them. I apologize. I apologize to all bromine and krypton fans out there. Superman's like, no, go ahead, skip it. I don't care. But Superman sucks, so we'll go back and do krypton. So, same thing. We'll do N max, which these are both 4. They both have the same shell. And you might look at this and immediately go, oh, this is going to be the winner. But remember, it's an exception, because it's in group 8A. So bromine must have the more negative electron affinity. I apologize again for skipping that. I didn't even see it. I just had a brain fart moment. All right, so now we'll continue. We're going to talk about the periodic table. So, as you can probably guess, based on all of the trends that we have observed so far in quantum mechanics, that the periodic table is really, really powerful at predicting things. So, like with ionization energies get higher as you go from left to right. They get lower as you go up top to bottom. And that is a trend that we can predict based on just two elements. So if I pick any two elements and I say don't use quantum mechanics to answer the question, you could say, oh, this element is further to the right. It must have a higher ionization energy. Oh, this element is further down. Its electron affinity must be less negative. Now, somebody in Russia figured this out and decided to arrange all the elements based on these properties that had been observed. And that was this guy. His name is Dmitri Mendeleev. And what Dmitri Mendeleev did was he created the very first periodic table. And so the periodic table organizes all of the trends that we have observed in a nice, concise place that looks like this. And so we can now use the table to make these predictive trends. Now, on an exam, what I'm going to do is I'm going to give you a bunch of quantum mechanical reasons for something. You're going to have to pick the right one. I'm also going to give you periodic trends, which are not quantum mechanical reasons. Saying that an element has a higher ionization energy because it is further to the right on the periodic table is not explaining what's going on. That's not a why. That's not even a how. That's a trend. Okay, so that would not be a useful answer on the quiz. But that being said, now that we have covered all the quantum mechanics and we understand what's going on, presumably, we can then fast track straight to, oh, I'm going to pick the one that's further down because it has the lower ionization energy, or whatever trend we're trying to do. Now, we've used this terminology already, periods and groups. All you really need to know is that groups go up and down. They are columns. And then that periods go across. They are rows. As you've probably noticed, the period that an element is in represents the highest principal quantum number that is available to it. For example, anything in period 5 will have electrons in the valence shell n equals 5. For the groups and columns notation, we're going to talk about what those numbers mean in Chapter 4 when we start counting valence electrons. But any element that's in a given group will always have the same valence electrons available to them. For instance, anything in the group 2A will have something S2 as the electrons that we write at the end of its configuration. Finally, here's a bunch of names that we care about on the periodic table. So you'll want to know the names that I'm going to highlight, the group numbers in yellow. And really, these are the ones that matter that I've done here. So chalcogens and pnictogens, I'll be honest, 2 years ago when we started using this textbook, I had never heard of pnictogens. So pnictogens is just an esoteric name. I heard chalcogens in grad school because I worked in a lab that specifically was trying to do reactions with oxygen and sulfur with metals. But that is so uncommon that I've never seen it outside of that. That word halogen, however, you hear halogen all the time. So you've probably heard of a halogen lamp, for example. Or you do halogenation reactions. And then the other stuff is just common enough that you should know it. So alkali metals are group 1. Alkaline earth metals are group 2. Halogens are group 7 or 17. 7A, I should say. Noble gases are group 8A or 18. These elements down here, I'm just calling them the lanthanides and actinides, and the only reason that you need to know these is because I studied them. That's really it. You don't actually need to know those down there, but you do want to know the transition metals. Transition metals is a very commonly used term because transition metals are abundant and used in a lot of chemistry. Whereas lanthanides and actinides, we use them in TVs, and we use them in nuclear power. But other than that, there's not really much that we do with them yet. You could do this experiment on your own. I don't really care about it. I do want to quickly go over metals and nonmetals real fast, though. Just so I can put Bender on the screen here. A metal is going to be defined as anything that has these traits to it. Metals are conductive, both electrically and thermally, so they conduct heat very quickly and easily. They are malleable or ductile, which means that if something is malleable, you can hit it with a hammer and it gets thinner and thinner and thinner. If it's ductile, you pull on it and it becomes a wire that is a thinner and thinner and thinner gauge. And then finally, metals are shiny. Just like Bender. Now, if you are a non-metal, you have none of those properties. So you are not thermally conductive, you are not electrically conductive, you are not malleable or ductile, and you are not shiny. Iodine, shown over on the right here, if you hit it with a hammer, it shatters. It's not shiny, you can't conduct electricity with it. It just does completely different things. Some substances on the periodic table do some of these things, and those are specifically called metalloids. Now, these substances are valuable to us because we can manipulate their properties. For instance, silicon is a metalloid and has limited electric conductivity. That is useful to us because it does conduct electricity, but it does not conduct it extremely well. If it was super good at it, then we couldn't make computers out of it because all the computers would overheat and they would get really hot and then they would melt, and that would be very difficult to make a computer out of. On the periodic table, elements are arranged in such a way that the non-metals are on the right, over here. The metals are on the left, over there, over here. And then in the middle, we have the staircase, which depending on the periodic table that you are using, you may or may not be able to see. On here, it's pretty obvious. It's this right here. I'm going to draw it in with whatever color I've selected. This staircase is called the metal-non-metal staircase. And what that basically means is that anything touching the metal-non-metal staircase is a metalloid. With two exceptions, as you can see. Actually, there are three exceptions. And now that I've said that, we only really care about this one. This is the exception. Aluminum is a metal. We don't care about polonium or actinium. Or not actinium, sorry. Astatine. Because they are radioactive. But everything else that is not aluminum touching that metal-non-metal line is a metalloid. Now, of course, you can reference this during the test. So I'm going to just ask you a question like, choose the one that's a metalloid. And then you look it up on the periodic table, which one's touching the staircase that isn't aluminum. And I believe that's the end of that section. Oh, and just here's some pictures of metallic character going from right to left and top to bottom. Things get more metal as you move left. They get more metallic as you move down. So some pretty pictures for you to look at. And I believe that's the end of that section. That's why I wanted to do that really quickly. So when we come back on Tuesday, we're going to talk about something very different from quantum mechanics. We're going to talk about how we define compounds as ionic or molecular. And then we're going to start building salts. And then we're going to start drawing bonding and Lewis structures and stuff like that. So we are finally free from the clutches of quantum mechanics. We're not done with Chapter 3 yet, so we're going to have the depressing music for one more day. But that's it for today. I want to thank everybody for watching. If you have any questions, let me know in the chat or over email. I'm happy to answer them. I realize that this stuff is very difficult. really the only way to master quantum mechanics is just to ask a lot of questions and to do a bunch of practice. Oh, we can go back to the pictures. Like, there you go. We'll leave them on the screen for you for just a little bit. If you watch Steven Universe, yes, this is bismuth, and yes, bismuth's gem that she has actually looks like bismuth. And then here's the other metals if you want to see them. But this is all in the slides. That's actually why I like to talk about that page, because then I can talk about Steven Universe, which is actually a good show. Where am I? I want to go to here. All right, so yeah, that's it for today. I will catch everybody next week. Quiz number 3 will be up at some point, probably before we finish the chapter, just so I can have it out there. It will still be due a week after we finish the chapter. So expect that soon. Send me an email if you have any questions. Stay healthy, stay safe, stay at home.